Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about the relation between linear quantities and their angular quantities. For example, we said for tangential speed, it is equal to angular speed times the radius. For tangential acceleration, it was angular acceleration times the radius. And based on those two, of course, we said we could do the same thing for displacement. Delta x, it is equal to angular displacement times the radius. Today, we'll talk about a different concept, and that is centripetal acceleration. What is centripetal acceleration? When an object moves in a circle, obviously, the direction of the motion continuously changes. The result, or because of that change in the direction of the motion or in the direction of the velocity, that leads to an acceleration, and that acceleration it is called centripetal acceleration. Let me tell you more of what I mean by centripetal acceleration. It is sort of clear from its name that it is an acceleration that is always directed towards the center here. Consider, for example, an object moving in a circle. At some point here, let's say this is the direction of the tangential speed, let's say, and then at some other points, let's say the direction of the tangential speed would be somewhere here, let's say at this point. At another point, this will be the direction of the tangential speed, and this is the direction of the tangential speed at this point. But no matter what the point is, there is always centripetal acceleration, which is directed towards the center, no matter what the point you're taking. So this is exactly what we mean by centripetal acceleration. It is always directed towards the center. So we said this is tangential, okay? These are tangential. When an object is moving in a circle, clearly the direction of the motion changes. And you can see that, but the centripetal acceleration, it is always directed towards the center. But remember one thing, if the direction of the centripetal acceleration is always directed towards the center, can we say the direction of the centripetal acceleration is constant? No. And why is that? Because at this point here, the center is to the left, all right? At this point here, all right, the center is, you could say, downward, or you could say south if we look at this one here. At this point, the center, it is directed to the right, let's say, or east, you could say. And at this point, the center, it is towards the north, if we call this side is north in here. So it is true that it is always directed towards the center, but the center is at different, let's say, views, or let's say a different direction at every single point here. So that is basically the direction of the centripetal acceleration here. So why do we have this? Okay, remember, centripetal acceleration, it is the variation as a definition, or you can say it is the variation of the direction of the velocity, okay, and then divided by the time, or the time rate, if you want to put it precisely. We'll say the time rate of the variation of the direction of velocity, that is for second, it is always directed towards the center, and third, it is measured in meter per second squared. So we can say as a definition, or as an equation, we have an equation for that. We can say centripetal, it is equal to tangential squared divided by the radius here. Remember this, like, where does this equation come from? It is not required from you, so just remember this. But sometimes in order to help my students remember this better, I'll just do this one. We'll say centripetal acceleration. Then we said earlier that anything that it says the time rate, that means something divided by the time. Okay, and then the time rate of the variation. What does the variation mean? It means the change, right? The change of what? Of the direction of the velocity. Sometimes I'll just do this one, like just to help them remember. Once again, this is not the equation that we're going to use for centripetal. This is just a help, or something, let's say, to help you remember this. That'll be the time rate of the change of the direction of, you see this arrow here, just to help you remember the direction of the velocity change over the time. That is called centripetal acceleration. But once again, that is not an equation to use in calculation. This is the equation. So at this point on, remember this, hereafter, whenever we say an object is moving in a circle, there will always be centripetal acceleration no matter what, as long as the object's moving in a circle. Whether the motion is, for example, whether the object speeds up or slows down, doesn't matter. Even if it doesn't speed up or slow down, even if it is moving at a constant velocity, let's say speed, the object will always have centripetal acceleration. So remember this, we can say whenever an object is moving, let's say in a circle, let's just say object, okay, moving in a circle, moving in a circle. course, there are two possibilities here. Let's say if it is moving, of course, it is either moving with a constant speed, right? That means it doesn't speed up or slow down, or the speed could be changing here. Speed changing, let's say. Okay, remember this, if the speed is changing now, we have two types, let's say, of acceleration at this point. We have centripetal and we have tangential. Whether the speed is changing or not, we know that if the speed is constant, that means V initial, it is equal to V final. At this point, we can say there is no tangential acceleration, don't forget. Because tangential acceleration, it is equal to V final minus V initial divided by delta t. If these two are equal, then of course we get 0 over delta t. No matter what the delta t is, it is always 0 at this point here. So remember this, whenever it says constant speed, remember there is no tangential acceleration. But can we say the same thing about centripetal acceleration? No, there is always centripetal acceleration. Why? Because the direction of the motion is always changing, regardless to whether the speed is changing or not. So there is always centripetal. What about if the motion is changing? If the motion is changing or the speed is changing, in that case, of course, there will be, for example, V initial will not be equal to V final, so there is tangential acceleration here, and of course there is always centripetal acceleration as well here. So remember this now, whenever it says an object moving in a circle, remember this. It is either the object is moving at a constant speed, constant motion here, which means that we can say that the angular, let's say the tangential speed and, or let's say tangential speed initial and final are equal, so there's no tangential acceleration. There's one more point, by the way. If it says constant speed, that would also lead to, let's say, a constant angular speed as well. So omega initial would equal to omega final. In that case, we can also say there is no angular acceleration too. So remember this, when it says constant speed, that means tangential is 0, angular acceleration is 0, but there is always centripetal here. What about this one here? If the speed is changing, of course we can say there is tangential. There will also be angular acceleration as well if we ever interested, but we normally mostly talk about tangential acceleration and centripetal mostly here. So we're not going to talk about angular acceleration that much, but just remember, if the speed is changing, of course, this one is going to be different as well. But then there will always be centripetal acceleration. Why? Because the direction of the motion continuously change, and that is what I need you to remember whenever it comes to object moving in a circle. That is regarding this one now. So let's talk about the equation a little. Okay, when an object is moving in a circle here, so this is, we said there will always be centripetal acceleration. So this is the equation that we use for centripetal acceleration. You can say actually this is one of them here. Now there is another equation here, which is also, we can say centripetal, that is equal to omega squared times the radius. Where does this equation come from? Now we have learned previously, okay, we know that in the previous sections, we said tangential, it is equal to omega times or angular times the radius. If I make angular the subject, that would be tangential over the radius, yes? So if I substitute this into this equation here, remember that is the main equation, but if I just want to substitute, that would be what? That would be omega squared times radius squared divided by the radius, yes? Then you can see that one cancels out with this one here, so what are left in the equation now? That is omega squared times the radius. This is also one of the equations that we have. So these are the equations that we use for centripetal acceleration. There is one more equation which is the least popular. We don't have it in the book, but just in case, because we can get this equation as once we substitute. So it is also good to know, even though we don't have any question or let's say questions, that we can use them this. So in that case, we can say centripetal that is equal to tangential times angular. Now, where does this come from? Now, remember this equation here. If I make r the subject here, r would equal to what? Equals to tangential over omega. Do you agree? Yes, well then. So now let's substitute this r into this equation right here. So what will we get as a result of this? We'll say centripetal, in that case, that is equal to tangential squared divided by tangential over omega. One of the tangentials cancel out with this one. This omega goes to the top. So centripetal that is equal to tangential times omega. Like once again, this is the equation that we get by substituting this to here, even though we don't have any equation to solve or to use this equation for, but because we can also get this one too, so why not? I think it's knowing this one is also nothing bad here. But these are the two equations that we will focus on them the most. Okay, now that is for this one too. There's one more thing I would like you to know. Okay, remember those. How do we get acceleration, or when do we have acceleration? Remember, we can have or get acceleration in three different ways here. So we can say acceleration, right? It can be obtained or achieved by three different methods here. The first one is, do you remember last year we said if an object speeds up or slows down, there will always be acceleration, yes? So we can say by changing, let's say, the magnitude, by changing the magnitude of velocity, right? The magnitude of velocity, which means that by increasing the velocity or decreasing the velocity, we can have acceleration here. What about another method is by changing the direction of, by changing what? The direction of the velocity, or you can say motion. The direction of motion. And what do we mean by this? For example, if an object is moving in a circle here, does the direction continuously or always change? Yes. Even if the magnitude doesn't change, because the direction is changing, that means still you have an acceleration, don't forget. So you'll have acceleration in these cases. What if both of the magnitude and the direction are changing? Of course, then we have acceleration as well. So by, let's say, changing both, right, the direction and the magnitude. Let's say the magnitude and direction. The magnitude and the direction of the motion. The direction of motion. So these are the, for example, ways we can have acceleration. And of course, we have a very good question, let's say, and sometimes it's a bit tricky to some of the students. It talks about, for example, we know, let's say it says the gas pedal of a car. We know that if you press the gas pedal, it makes the car speed up. And if it is speeding up, then the object's, let's say, magnitude or the object's motion is going to change, let's say, or the speed will change. So at this point, we can say we have acceleration. What does the brake pad does? Once you press the brakes, it makes the car slow down, yes? Very good. So we can say both pressing on the gas pedal or pressing on the brake pad, it makes the car accelerate or decelerate. In other words, we have acceleration in that case. But does the steering wheel make the car, or the question says, does the steering wheel can do either or perform either of the two? The answer is yes. Don't fall for this, by the way. Even though the steering wheel, you might just think the steering wheel never makes the car go forward, let's say faster or slower. I agree with you, right? But here's one thing you have to be careful. Even though the steering wheel does not make the car go faster or slower, but can it make it change direction? Yes. If it can change direction, can we have, or do we have acceleration? Yes. So remember this, acceleration can be achieved by one of the two, either by changing the speed or changing the direction. And of course, if both of them change, that is even better at this point. But remember, that is the reason why whenever an object is moving in a circle, there is always centripetal. Even if the speed doesn't change, okay, that is totally fine. Because the direction of the motion is changing, there will always be centripetal acceleration. This is why we can never have an object moving in a circle without centripetal acceleration, because the direction is always changing here. So there will always be centripetal acceleration. All right. So once again, we said, what is the definition of centripetal acceleration? It is the time rate of the variation of the direction of the velocity. It is always directed towards the center and always measured in meter per second squared. So remember, like the keyword here, we only have one keyword which says it is the variation of, or the rate of the variation of the direction of velocity. Whenever it says the variation, which means the change here, the change of the direction of velocity, that of course, clearly, that is centripetal acceleration. Don't forget, you can underline the keyword just to help you remember. Okay, it says always directed towards the center of a circle, which is always measured in meter per second squared. This is the equation we just said, for example. Centripetal, it is equal to tangential squared divided by the radius. Don't forget, when do we use this? If tangential is given or required here. And then by substituting this, we can get this equation here. AC, it is equal to omega squared times R. And we said this is the least popular. We don't have this as an equation in the book, but by substituting this, we can get this one. So it is also good to know, but it is not mandatory. Okay, now we also talked about this one, how we can achieve acceleration, or how acceleration can be produced. We said it can be produced by two main ways, let's say, or two different ways: by changing the magnitude of the velocity, by making the object speed, or by making the object speed up or slow down. So when an object speeding up or slowing down, let's say, then there is a change in there is a change in the speed. Of course, we will have acceleration here. And then another way is by changing the direction of the velocity here. We said when the direction change, then of course there is centripetal acceleration, or acceleration in general here. But if we change both of them, that's even better. There's one thing I would like to point out, perhaps maybe with this one here. Let's go through this one, and then after that we'll talk about this one here. What is this piece of information saying here? It says when the delta t is very small, as delta t approaches 0, we can say V initial will almost be parallel to V final. And then, of course, the delta V, that is the change in the direction of velocity, will be approximately perpendicular to them, which is pointing towards the center of a circle. This means that the acceleration will also be directed towards the center of a circle, because the change of the direction of, you can say, the velocity here. We just mentioned that the direction of centripetal acceleration is always directed towards the center. But have you ever wondered why, or what causes or makes this? Let me tell you the idea behind this one here. But before that, let me just tell you one thing here. Or perhaps maybe I'll just tell you this, then I'll tell you the angle between, for example, tangential speed and acceleration, and then what happens if the object speeds up or slows down here. But first, let's start with this one here. Let's say we have an object, or let's say an object moving in a circle. We have an object moving in a circle. And that is what we have. Consider the object is moving. We know that here's, let's say, one of the points where the object's moving here. At a point, the direction of the motion here is in this way. Can I call it V initial? Yes. At some other points here, let's say, we'll make the time very short. So in this case, of course, let's say this is the other direction of the motion at this point here. Okay, now remember this. This is V initial because we start at this point here, and you can call this one V final here, because the time that we're taking here is very short at this point here. So what would be the change in velocity here? If I want to find the change in velocity, I'll try to do it here, or maybe there. Okay, because it's easier, clear to this one. So the change in velocity, it is equal to V final, and that is of course a vector, V final minus V initial. Okay, now, can I rewrite this equation this way? V final plus V, let's say, plus minus V initial. Let me tell you the reason why I'm writing this one here first. Now, in grade 11, of course, you've learned that if a vector that is going, let's say, to this side, let's call it A, right? That is positive A. What about if I say negative A, right? If it is negative A, it is the same exact vector, but it's just moving or pointing in the opposite direction. Isn't that what it is? Yes. So let's use this right here and see what happens here. So if we want to find the difference between the two here, remember now at this point it is, we can say grade 11. And also we said that if, let's say two vectors are in the same direction, we add them opposite direction, we subtract them if they're at some angle here, we just connect them head to tail and see what is the resultant vector here. So just remember this. Positive A this way, if it is negative, it is going to be the same vector, it is just changing the direction. So this is the reason why I did this one here. So this is, in this equation, of course, it says V final, and this is exactly what V final is. And then minus V initial. So at this point, I'm going to keep, let's say, V final here first, but for V initial here, because the question says minus V initial, so what would be minus V initial at this point? Same as we cannot do this one here. So can I say V initial? Let me see if I can only do this one here. It seems I cannot do that. because it is attached at this point here. So I'll just erase this one. But before I do here, let me tell you this. About or regarding this one here, if V initial is positive to this way, what is there that I have? It says minus V initial. So it is going to be the same exact vector here, but it is going to be in opposite direction. So I can call this one, this is, let's say, negative V initial. So if that is the case here, all right, let's just bring this one here, and then this is what I'm going to do here. So if that is the case, you can see that. So this is how we add vectors. Remember, if one vector is in this direction, that is last here, right? And then there is another vector, for example, we just connect them head to tail, and then we'll find the resultant here. But what is the resultant at this point here? Remember, to find the resultant, we'll just connect head to tail. And let me erase the other vector here so that it doesn't confuse it now. So this is what I have. Remember, this is V final, okay? And this is V initial at this point. Now, look, do you see the direction of, for example, the resultant vector here? So this would be V final, which is always directed towards the center of a circle. Maybe my diagram is not that perfect at this point, but this is how it is done. So you can see that this would be, my bad, this is, let's say, the change in the direction of velocity here, which is always directed towards the center. Let me give it a try one more time real quick, see if we can get this one right. So I'll draw this one here at this point, just so that we could see the difference maybe more clearly. So let's say this is V initial, and then at a point here, we'll just draw it here, this is V final, okay? And then based on the equation, it says V final minus initial. So we'll keep the final the same, and then we'll take the first vector here, which is V initial, and then we'll just take the reciprocal here. Now, that's a good thing. Now I could do that here. Let me first copy this one. Okay, and then I'll just flip this vector so that we know it is the same vector. We'll just change the direction here. Is that the same thing? Let's keep the direction the same. So this exact same vector, but we're just changing the direction. Now, I'll connect this one here. Let's just extend this one a little bit so you can see that. Now, I'll just erase this one. So, but before I do here, once again, based on this equation, it says final. So this is V final. Right, minus initial. Remember, initial was like at this point, but if it says minus initial, that means negative initial, which means the same initial, but this time is going to be negative here. So when it says negative, remember it changed direction now. And if you draw a diagram here, you will see that this would be the resultant between the two, or you can say delta V. Isn't that directed towards the center of a circle? Now this diagram is better. So no matter at what 2 points you do, you'll always see that delta V, the resultant velocity, is always directed towards the center. So that is the change in velocity. But of course, this change happens over some time, yes? So the change in velocity divided by the delta time, that is the centripetal acceleration. You could do it at any other 2 points. For example, this is the reason why centripetal acceleration is always directed towards the center of a circle. Okay, now that'll be for that. Remember this. Now, let me tell you one more thing regarding centripetal, or perhaps the angle maybe, let's say, between tangential, centripetal, and all that. Remember we said if an object is moving in a circle, okay, let's say this is the direction of the tangential, and this is the direction of centripetal here. Now, if I ask you a question here, we said centripetal, it is always directed towards the center, this tangential. And if I ask you, what is the angle between tangential and centripetal? Do you see this right angle between the two? So we can say tangential, it is perpendicular. This is a symbol, it means right angle, Masha. So perpendicular to what? To centripetal acceleration. So what if I have, for example, tangential? That is, what if I have tangential acceleration as well? Remember, the angle between tangential and centripetal also, it is right angle, or you can say 90 degrees as well. So you could say this is, it means 90 degrees. So don't forget that is also 90 degrees here. Okay, but what is the angle between tangential acceleration and tangential speed? We said the angle between the two is 0 degrees, unless if it says slows down. If it slows down, the tangential acceleration with the tangential speed is going to be 180. So let's just say in terms of slowing down, the angle between tangential acceleration and tangential speed is going to be 180. But when do we use this? Only if it clearly states that the object slows down, for example. Okay, but what is the angle between centripetal acceleration and tangential? No matter whether the object speeds up or slows down, it is always 90 degrees. So it is never going to be 180. So we don't care about speeding or slowing down here. Okay, so let's summarize what we have learned so far. We said centripetal acceleration, it is the time rate of the variation of the direction of the velocity, or the time rate of the change or the variation of the direction of velocity. It is always directed towards the center and is measured in meter per second squared. And then we also said that why the centripetal, it is always directed towards the center. We just stated the reason why, because the direction of delta V, it is always directed towards the center here. And clearly this change happens over some time. So the change of the direction of velocity over the time, that would be centripetal acceleration here. And we also learned about the equations as well. All right, now let's get back to what we had, and perhaps maybe answer a few Wizati questions at this point here. So this is the explanation of what I just told you about. For example, remember we make this one negative. It's clearly negative minus V initial, so minus this one here. So that would be 2 points here. So the direction or the resultant of this one would always be directed towards the center at this point here. And also remember the keyword regarding the definition. Do you see this one? It says the time rate of, okay, the time rate of what? The time rate of the variation of the direction of velocity. So whenever you see the direction of, or the variation, which means the change of the direction of velocity, that is centripetal acceleration. Okay, the angle between, this is one of the questions that you also need to know. The angle between the direction of tangential acceleration and centripetal. Remember, you can always draw the diagram to help you. This is, it says tangential acceleration. So here's tangential and here's centripetal. So what is the angle between the two? It is 90 degrees here. Okay, and then this one says which of the following equation is correct to calculate centripetal acceleration? Remember, this is incorrect. Okay, this is incorrect because it has something we haven't even studied yet, that is moment of inertia. What about this one here? It's supposed to be quite opposite of this one, V tangential, right? So not this one. What about this one, tangential over the radius? That is the correct one here. All right, so let's start with a few questions maybe. All right, so one of the practice, or you can say sample problems that we have, it says, a test car moves at a constant speed. Remember what I told you earlier. Whenever it says constant speed, that means there is no tangential acceleration. But can I say there is no centripetal acceleration? Never. Okay, as long as it is moving in a circle. And also says, if the car is 48 meters from the track center, that is also a keyword, and I need you to take a note here. Whenever it says this much far from the center, that number, it is going to be the radius here. So this is the radius, okay? And it says has a centripetal acceleration. So remember, this is centripetal. What is the tangential speed? We said for centripetal now we have two equations, right? Centripetal, we can either use, let's say, tangential squared over the radius, or we can use, let's say, omega squared times r. Which one of these two am I supposed to use at this point? Because it talks about tangential speed, so this is the one that I need to use at this point here. So we'll say centripetal. It says, what is the tangential, correct? So once again, centripetal, it is equal to tangential squared divided by the radius. You need to cross multiply. So tangential squared, it is equal to AC, or centripetal, times the radius. But I need tangential. I don't want, let's say, tangential squared. So we'll just take the radical for both sides, yes? So that'll be this to cancel out. So tangential, it is equal to the square root of centripetal acceleration times the radius. Now all you have to do, just plug in the numbers. That is 8.05, all right, multiply by the radius, which is 48.2, and then you could just, of course, get the answer, which is going to be 19.7. Since it is tangential, it is going to be meter per second, and that is the answer. So clearly, these are very easy if you know what you're given and what is unknown here. There is another question which is similar to what we have just solved. It says a race car moves along a circular track, and let's say it has an angular speed. This time we have omega, or angular speed of 0.512 radian per second. If the car's centripetal acceleration, so here's centripetal acceleration this much, what is the distance between the car and the center of the track. Remember I told you, whenever it says what is the distance between this and the center of the track, they're basically asking about the radius here. So once again, we'll say centripetal, it is equal to angular times the radius. Now, you can, of course, rearrange the equation. The radius, it is equal to centripetal acceleration divided by omega. That is as simple as this. And that is 15.4, that is the centripetal, divided by 0.512. You do the math, of course, you will get 58.7. Since it is the radius, it is going to be in meters. See how easy these questions can be? Sometimes the questions are very easy, especially, let's say, if somebody's not very good, they'll try to help them at least to reach perhaps 50, and these are one of the questions, or you can say some of the question that might be given to them here. There's another question which is also very similar to what we have just solved. It says a piece of clay sits 0.2 meter from the center. So is that the radius? Yes. Of a potter's wheel. If the potter spins the wheel at an angular speed, so this is omega, this much radian per second, what is the magnitude of the centripetal acceleration, all right, of the piece of clay on the wheel here? So now because we're given omega and r, so centripetal, we can say it is angular speed squared, right? So angular speed squared times the radius. So once again, that is 20.5 squared times the radius, which is 0.2. You do the math, of course, you'll find AC, which is equal to what? 84 meter per second squared. So these are the kind of questions, very easy. You can do them without any problems or any struggle at this point here. All right, let's talk about or go to another question. This is also an easy question here. It says a building superintendent twirls a set of keys in a circle at the end of the cord. Okay, let's just remove this one here. At the end of the cord, okay, says at the end of the cord, the keys, wanted to remove this one, but it seems it didn't help much. So let's just move this one a little bit lower. Okay, so the keys have a centripetal acceleration, so there's AC, okay? And the cord has a length of this much here, which is this. You might say, what does the length has to do with this? What is the tangential speed in here? So V tangential is unknown. Let me give you an idea. Imagine this set of keys is just a piece of mass. So the length of this cord here, that is the length. Once you're doing that, for example, think or imagine you have a tasbih and there's something attached at the end of the tasbih at this point here. So once you're moving this, let's say in a circle, so this length, all right, of the cord at this point, it becomes what? It becomes the radius of the circle, because this thing, it is going to move in a circle, so that length becomes the radius. So this is clearly the radius here. Okay, so now the tangential is unknown. So do exactly what we've done before. AC, it is equal to tangential squared over the radius, cross multiply. Tangential squared, it is equal to centripetal acceleration times the radius. We want tangential, so take a radical for both sides. That'll be the square root of centripetal times the radius. Do you have the centripetal? Yes, it is 145. So that is 145 times. What is the radius? The radius is 0.34. Okay, so just do the math. Of course, you'll find the answer. Don't forget to take the radical, and that's it. So this is the AC, this is the radius, and then the answer is going to be about 7 meters per second, and that's it. So easy peasy. All right, now this is a very good study tip actually. Up to this point, we have studied 4 types of acceleration. What are these 4 types of accelerations? Now the first thing, for example, let's just say types of acceleration. All right, up to this point here, okay? The first type that we've studied was, let's say it was in grade 11, you could say, right? And that is, you can say gravitational, right? Gravitational acceleration here, or you can say AG here. And the value for gravitational acceleration, sometimes we use G for that, and that is 9.81 meter per second squared. That is the first type of acceleration that we have studied. Now, the second type of acceleration was the first type of acceleration that we studied this year, and it was angular acceleration. Do you remember what was angular acceleration? It was you could say the change in angular speed divided by the time, or you could have said omega final minus omega initial divided by delta time. And it was measured in radian per second squared. That was the second type here. Okay, and then the third type of acceleration, all right, that we have, it is the tangential acceleration, which is equal to angular acceleration times the radius. And then this one was measured in meter per second squared here. So let me tell you this. This is for an object that is moving in a straight line. Not a straight line, actually. If it goes upward or goes downward here, sometimes we call it free fall acceleration. All right, that is one thing you could say. And then this one, if an object is moving at a circle here, so let's say this moving in a circle here, we have angular acceleration. For the third one here, let's say tangential, if an object is, that will be the link between tangential acceleration, let's say angular acceleration, let's say, and tangential acceleration, that'll be the link between the two. And then we just studied the fourth one here, which is centripetal acceleration. What is centripetal acceleration? It is when an object is moving, we can say at a circle here. We said it can be found by two different methods here. We can say tangential squared over the radius, or omega squared times the radius. That is once again for an object that is moving in a circle, there is always centripetal acceleration here. And these are, of course, centripetal acceleration that is measured in meter per second squared. So how do I know which one of these do I need to use? That depends on the question, or just the context of the question, you could say, at this point. But so far, these are the types of acceleration that we have studied up to this point. Okay, there are some questions here, and these are basically what we have. Okay, there are a few questions. These are very easy, of course. We've done questions like this, but let's try at least, let's say, one or two at this point here. Maybe this one. This is 50 meter. It says, how far? Let's try this one first. It says, a car moving in a circular path at a constant tangential speed here. If this is tangential, yes, this is VT here. If the car is 50 meters far from the center, that is the radius. It is in meters, so no conversion needed. It says it is centripetal acceleration is what? So this is pretty easy. We could say centripetal acceleration, it is equal to tangential squared divided by the radius. So just divide 20 squared by 50, you will get one of these answers, and then that would be it. This one, I guess, that is also easy. It says, what is the tangential speed? We've done this one there. And then this one is also very easy. It says, what is the centripetal acceleration of a person standing 12 meters from the center of the ride? So that is angular squared times the radius. You can also get the centripetal acceleration. That is easy enough, I believe. Okay. All right, now let's talk about this one a little. What does it say? Centripetal and tangential acceleration are not the same. Now at this point, I need you to be a little bit careful because I already gave you a note regarding this one. We said if an object is moving on a circle, but whenever it says constant motion, don't forget. What does it mean if it says at a constant speed, let's say? We said whenever it says constant speed, right? That means, of course, V initial, it is equal to V final. So tangential acceleration is 0. And even if it is moving in a circle, we can say omega initial, it is equal to omega final. Then angular acceleration is also 0. But if an object, whether the speed is constant or not, because it is moving in a circle, there is always centripetal acceleration. Remember this, there is always centripetal. So we can never ever have an object that is moving in a circle without centripetal. Okay, so once again, we said if it is only, or if it has constant speed, then that object would always, let's say, experience centripetal acceleration. Okay, if an object moving in a circle at, let's say, at a constant speed, there will always be only centripetal acceleration, but tangential, it is going to be what? It is going to be 0. So there will only be centripetal acceleration. But if you look at the second point, when a car is moving at a circular path with changing speed, don't forget. So if the speed is changing, then of course we have tangential. And then of course there will be angular too if you want to find angular, even though we're not interested in angular. But there will be tangential and there will always be centripetal as well. That is for changing speed. So these notes, of course, you might benefit from these two a lot. So remember that. Now there is also one more point, which is tangential and centripetal acceleration. If we have them both together, then we just say, for example, this one is a very interesting point, actually. I need you to focus very well at this point here. So here, let's say we have an object that is moving at a circle here. So we said if the object is moving at a circle, there is always centripetal, yes? So here is AC. And then if, let's just draw maybe two nice arrows here at this point. Okay. So here's one of them. Let's say if an object is moving in a circle, there is always AC. And then if the speed is changing, can I say I have tangential as well? Yes. So what do we do if we have both centripetal acceleration and then if we have tangential acceleration as well? So these two are perpendicular to one another. If you remember last year in grade 11, we said if two vectors are in the same direction, we add them, yes? Okay, so that'll be a bigger vector. If two vectors are in opposite direction, we're going to, let's say, subtract them here. So one here, one there, we'll just subtract them. Okay, but if they're in the same direction, we add them. What if they are at a right angle? Do you remember we said if they are at a right angle, we're going to use Pythagorean theorem. But how do we do that? First, we'll have to connect the two vectors head to tail, and then we'll find the resultant here. Okay, this is basically the resultant. We can even find the direction here. We said for the resultant, we'll use Pythagorean, which we can say, let's call this side A and call this side B. You can call the resultant C, doesn't matter. We'll say a squared plus b squared. And for the direction, we use theta. It is equal to tan inverse of opposite over adjacent. Now, I need you to be careful at this point here because there is something interesting you need to know. So what would be the resultant at this point? Before we find the resultant, we'll have to move one of the two vectors. Please let me change this vector. It doesn't allow me to move one vectors alone here. So here's the thing. What about this one here? Let's give it a try. No, it doesn't work. Okay, so if I ever want to do that, let's just erase this one perhaps, maybe. Okay, no, it doesn't allow me to do this. All right, so at this point here, I think I'll have to erase the whole thing maybe. Okay, that's not important here. Okay, so I'll just read, I should have done the hours differently here. Give me a second. All right, so that is, let's say, one of them. Oh, this one's still here. Okay, that is one of them. Okay, that's attached to this. All right, so we'll just move this one here. I'm not going to connect them so that I can move these vectors separately. It doesn't work, actually. Okay, I'll just do using bare hands at this point here. So remember, that is centripetal, right? And this is tangential. This is what we have, okay? So look, now how do you find the resultant? We have to connect the vectors head to tail. That's a very easy thing here. So that is easy, no problem with that. So, but which one of these vectors, for example, do I need to connect them head to tail? Should I move AC, let's say, to the top, or, like tangential, bring it here, let's say, at this point? Well, that is a bit tricky at this point, and I don't want you to make mistakes at this point. Look, do you remember in grade 11, we said whichever the vector started first, you have to move the other vector, for example, if you had two vectors, or there's another way you could say. We were also saying the angle always starts with the first vector that we started here. So in other cases at this point here, this point we can say we'll have to move the AC here. Right? So that is, I should have kept it at this point, by the way. So we're just going to translate or move this one, this AC, right up to this point here. So we'll just move this AC. We're going to write it here. By the way, it has to be the same vector, right? We'll just move this one upward here. If I move this one upward here, then this AC will be gone at this point. So if I want to find the resultant, okay, this is going to be, let's say, the resultant here. Let's just move this one maybe. This would be the resultant here. That is the resultant. Okay. So in order to find the resultant, we'll say R, it is equal to, at this point, it is not a problem. We can say tangential squared plus, this of course would be AC here, and then plus AC squared. Now, Here's one thing that is very important. What about the direction here? We'll say tan theta, it is equal to tan inverse of opposite over adjacent. Okay, so this will be the angle, right? But why would be this or this would be the angle here? Perhaps I should have started, like we're telling you this a bit earlier. Like if an object is moving in a circle, just think about this one here. If an object is moving in a circle, if I take a small section right at this point, this is also another reason why we're using, or let's say moving AC. Basically, this tells you which vector starts first. If you ever want to start moving in a circle, don't you have to move at least, for example, if the time is very short, aren't you moving in a straight line first? Then after moving in a straight line, that is clearly tangential acceleration. Then you're changing direction and of course moving in a circle. So in other words here, you can say that this vector starts first and then this one starts second. This is the reason why we're basically transferring, let's say, or moving AC to the top in here, because this is the first vector that it starts with first. This will be the second vector. I'll repeat this. Why is this? In grade 11, we said the angle always, like keep the vector that starts first, all right, and then move the other vector here. Or also regarding the angle, we said the angle must always be with the first vector that you start with. So because this one, you can see that if an object is moving in a circle, if the time is very short, even if I take this much here, isn't that a straight line movement here? Yes, if that is the case, then because the object is changing speed, so that'll be AT first. Then from this, you change the direction and then you, of course, move in a circle. So once again, AT starts first, that's why I keep AT, all right, or tangential acceleration, I'll move centripetal acceleration there. So for the resultant, doesn't matter actually which one you move, but what it matters is the direction here. So now if I go back to this one, based on this, who's the opposite here? We can say the opposite is AC here. So we'll say AC over AT here, okay? So you could just, of course, memorize this one here, but I would really, rather you learn for example, the reason why we move AC, for example, because we simply could have used the other one too here. So this is AC, and then this is AT. Why not we did not move this one here? Because it's also possible, let's say, right? But in terms of, one more time, in terms of the magnitude, it doesn't affect or it doesn't change. So this would be the resultant here. But is this the angle that the object starts with? No. Is this the angle that the object, is this the resultant? No. So once again, because this starts first, then this would be, so we'll move the other one. So this is basically the line or the path that it takes. So the angle is with, we can say with the what? With the tangential. If that is the case, opposite becomes AC. This is adjacent here. So what do you do, for example, if they gave you this angle in Wazari here? So let's say this is 50 in this case. So you can always get, for example, this angle back if you ever need it, so that you can use that in calculation, just in case, Yani. So let's not talk about this one because I have other plans for this one at this point here. So now this is how we can find the direction, tan inverse of AC over AT, and it is always like this. Okay, now, what do we do, for example? So you could, of course, use different numbers at this point. Here's another idea. What do you do if one of these were unknown and you're asked to find the other one? Once again, let me just draw this one here. We said this is okay. Regarding this one here, let's change color. Okay, so once again, let's say this is AC again, and this is tangential. And we said, this is how you can find the total. It really doesn't matter at this point which one you move, because total, you just square them. This is total acceleration, all right? Total. All right, so once again, total acceleration, that'll be the resultant. That is the total here. Once again, we said we'll move AC at this point here. Doesn't matter, even if it doesn't change. This is exactly the same thing, okay? This is representing AC, so you can erase this one here. So the total would be the square root of tangential acceleration plus centripetal acceleration. These are both squared in here. For the direction, once again, it is the tan inverse of, it is basically start with this, tan theta, okay? It is equal to AC over AT, but we want the angle, so angle it is equal to tan inverse of AC over AT here. So if you ever needed the angle, you could just use this equation. You can skip this point or skip this equation at this point here. But here's another thing here. What if, let's just say, they gave you the total acceleration, let's say, which is, let's just say 100, and they gave you this angle. Let's just say this is 30 here. And then they were asking they ask you to find AC, let's say. Take a look. If one of, let's say, these are three variables, you could say, that is total, tangential, and centripetal. If they gave you two, you can always find the other one, right? Let's say they'll give you total and tangential. You can square both sides, and then you can find, let's say, AC. Let me give you what I mean here. So I'll give you total, right? That's what we have. And then you're given the tangential as well. Let's just say the tangential, it is 10 at this point. Can you find, let's say, the AC? Yes, we could do that. Watch this. So once again, we'll say the total, or based on that equation, it is 100. It is equal to the radical of tangential, which is 10 squared plus AC. How do you find AC? Well, first square both sides. Let's say if this is 100, we can say 100 squared, that'll be, like 10,000. That is equal to, and that is going to be 10 squared. That is, these two cancel out clearly, that is 10 squared plus AC here. And then AC squared though. If I want to find AC, we'll just move this one to the other side. So AC, it is equal to, or let me just start with this, 10,000 minus 10 squared, that is equal to AC squared. All right, at this point here, this is going to be 100, 10,000 minus 100, you find the answer. So we can say AC, it is equal to the radical of just this two in a bracket, 10,000 minus 100, then you will find the answer, and that's it. But there is a problem, for example, if out of all three, only if one of them is given, let's say, with the angle, what do you do exactly? So we can use this equation, or let's say, sometimes we can use this equation to find the other one here. But once again, if I'm given the angle and the total only here, can I find AC? Or can I find AT? The answer is no. So what will I do in this case at this point? Remember, okay, if I have this, I assume you already know this one here. If that is the angle, this is called hypotenuse, right? This is called opposite, and this is the adjacent here. So once again, if you're given the total, which is the hypotenuse in this case, let's just say it is 100, and then you're given the angle 30. What if I ask for the opposite? Opposite represents AC here. So I'll say, what is AC? For example, if total acceleration is 100, right? And then the angle is between, let's say, tangential and translational, tangential acceleration and centripetal is 30 degrees, right? So I'll say, what is the AC? Centripetal acceleration. Okay, so you can see that you cannot use the total, because in order to find AC here, you must have both total and tangential. Can you have two unknown in an equation? No. Can you use this equation? No, because in order to find, for example, centripetal, you need, let's say, tangential to with the angle so that you can find this one. So again, there are two unknowns, we cannot use this. So what can you use instead? Remember, we have three functions here. We have sine theta, which is equal to opposite over hypotenuse, right? And then we have cosine theta, which is equal to adjacent over hypotenuse, okay? And then, yes, that is correct. I thought I kind of like did them incorrectly. And then the third one, we have tan theta, which is also equal to adjacent, opposite, my bad, over adjacent. Opposite over adjacent here. So out of these equations here, which one of them do you need to find here? Remember, you're given the total. Total is basically the hypotenuse. That means you have the hypotenuse and the angle. Which one, for example, given the hypotenuse and the angle, allows you to find the opposite? Or let's just say this, which one of these functions has opposite in it? And that is sine theta, right? So if I choose this one here, can I find, let's say, AC here? Yes, sine theta, that is clearly, we can say sine 30, it is equal to opposite. What represents opposite here? AC, right? As you can see, that'll be opposite to the angle, and then divided by the hypotenuse, which is 100 at this point here. So if you cross multiply AC, it is equal to 100 sine 30 here. So can I use or find AC just by knowing the total acceleration on the angle? Yes, this is how you could do that. What if they were asking for, they gave me total and the angle, and they said, what is the tangential? This is tangential. What is the tangential acceleration? What equation can I use at this point? Well, you will have to use cosine, because cosine allows me to find the adjacent, which represents the tangential acceleration at this point. So you have the angle, 30. You have the hypotenuse, which is the total, the 100, the total. And then you can just find, let's say, the tangential acceleration. And clearly, we've mentioned this one. If we have, let's say, the angle tangential, and then you can easily find the other one, let's say, just in case. If you have the angle on one of the sides, you can find, let's say, the other side here by using this equation. Okay, but remember, if I don't have any sides, can I find, for example, let's say, can I have two unknowns here? The answer is no. So in order, remember these functions here. If at any point you could not use these two equations, there is always a possibility that, think about these equations, maybe you can use one of them just to find the answer. Right, I hope that was clear. If not, keep practicing until you understand these fully, so that hopefully maybe someday it will benefit you. Okay, that was also a bit new as well. So here I've mentioned that is basically if we have both of them, tangential and centripetal, then we'll find the total. But once again, why do we move the centripetal, let's say, not the tangential? The reason why, because that is grade 11. We keep the first vector that we start with, and then we'll move the second vector at this point. In order for an object, once again, to move in a circle, it must move in a straight line first, then it changes direction here. So we can say the tangential side is first, so we'll move the AC here. This will be the resultant. The angle is also always with the first vector. That'll be the angle. If that is the case, this is AC now. So this is opposite, and this is, you can say, adjacent to the angle. Then based on those two, you can make your calculation here. And this information, of course, just to help you, if one of the, let's say, hypotenuse is given, the angle is given, one of the side, AC or IT, were unknown, you can always use that to help you remember or to help you get the answer. All right, these study tips hopefully will be the last thing for today. Or for this session, says the object's velocity and centripetal change because the direction of their motion always change. Remember, if an object is moving in a circle, even if it says constant speed, does that mean the velocity is constant? No. Velocity has both magnitude and direction. Even if the magnitude of the velocity doesn't change, even if the speed does not increase or decrease, because once you're moving in a circle, the direction of the motion always change, so the velocity is never constant. Let me just remind you this diagram one more time here. Okay, so if an object's moving in a circle, you can see that even if the speed doesn't increase or decrease, because the direction is changing, the velocity is never constant. Okay, and then the next thing, the acceleration is the same, even let's say, because the direction of the centripetal acceleration is always changing as well, even though it is towards the center. But center is at different directions at different points. If the object is not in translational equilibrium state due to the presence of centripetal force, this one is also very important, FC acting on it. Sometimes we'll say if the object is moving in a circle, right, the object can never be at translational equilibrium. And what is the reason for this? Why the object can never be at translational equilibrium, or what do you mean by translational equilibrium? Because the object's direction is always changing, right? That means there must always be a force on the object. Can the direction of something or an object move out of it on its own? The answer is no. So this is the reason why, because the direction is changing, there must be a force on this object to make it change direction. So that is why we'll say the object will never be in translational equilibrium. Why is that? It will only be at translational equilibrium if, let's say, initial and final velocities are equal, and also if the direction always remain on the same line or the same path. Even if the speed doesn't change here, but because the direction is changing, so we can never say the object is at translational equilibrium. But later on we'll see that it is fine to be in a rotational equilibrium, That is, if the speed doesn't change and the direction of the motion is always counterclockwise or clockwise, so it stays like that without speeding or slowing down, that is possible to be at rotational equilibrium. But for translational, no, because it is not in a straight line, the direction is changing. So there is always a force on it. Point 3 says, in circular motion, the object always experiences both centripetal and, let's say, centripetal acceleration and centripetal force. We know that, of course, if the direction of the motion changes, there must be a force on it. Otherwise, why would the direction change on its own, let's say? Point number 4, we can say specifically in circular motion, tangential, or let's say tangential speed, right? Tangential speed. It is at right angle. This angle is symbol of perpendicular. The angle between tangential speed and centripetal is 90. Tangential speed and centripetal force, which we're going to study next, it is also going to be 90 degrees here. The angle between tangential speed and tangential acceleration, it is 0 if it is speeding up. So we said these two are always in the same direction, right? If it is speeding up, if it stays slowing down, then of course it's going to be 180 or opposite to one another, which is going to be 180 degrees, which I assume you already know this. And then point number 6 says the angle between AC and FC is 0. Just remember this. If it is both of them tangential and tangential, if it doesn't say slow down, it is 0. Centripetal, centripetal, that is 0. But if it says, for example, let's say tangential with centripetal, clearly the angle between the two is 90 here. Again, tangential and centripetal, these are not the same, so it's going to be 90 degrees again. When the object is moving on a horizontal circular path, remember, at a constant speed, if it says constant speed, there is no tangential, there is only centripetal, and that is, we covered this one here. The last, perhaps, few Zari questions here says, which of the following equations are true to express a relation between tangential acceleration and centripetal? You can see that we didn't have any square cover here. AC over AT, this is good. What about this one here? Says there is tangential equal to this two. No, that is incorrect. This one is also incorrect at this point here. Okay, so the only correct one that links the relation between centripetal and tangential at this point, that is the tan theta here. And then we have this question to practice for you. And then one more question says, what is the angle between centripetal and tangential? Remember, one more time, it says centripetal, that is AC, tangential, and then that is VT here, so tangential velocity. So the angle between the two is 90 degrees here. And I would recommend you try these two questions as well, and hopefully you can do them right. All right, let's go through these questions real quick. I thought it was the last thing, but seems there's few more things left. Find the tangential speed of a bowling ball swung at a constant angular speed, that is omega, on a rope that is 5 meters long. Once again, okay, these are very easy at this point here. We know that it says find what? Find the tangential speed in here. Remember, we have angular speed and then we have radius. So remember, tangential, that is equal to angular times the radius. Yes, you have this and this. You could just multiply them and you will find the answer. This one is very important, and I need you to take a note for this question right here. It says if an object has a tangential acceleration of 10 meters per second, the angular speed will which of the following here? So remember, this number is positive, right? So take a note. If it says acceleration here, that is the acceleration. If it says positive, right? So if the acceleration is positive, remember this. That means if the acceleration is positive, that means omega final must be bigger than omega initial. Yes or no? That's one part. What if I have, let's say, what if we're talking about angular speed, by the way? So even if for angular speed here, we can say omega final will be bigger than omega initial. And why is that? Because we know that this point here, remember this, tangential, it is equal to angular times the radius. Angular, it is equal to tangential over the radius. So the radius is constant. If tangential is increasing, of course omega is increasing as well, because these are directly proportional. So we can say omega final must be bigger than omega initial. What about if it is decreasing? It is opposite to this. That means omega, or you can say V final, it is smaller than V initial. And then for omega final will be smaller than omega initial. So in that case, if it is, let's say, slow, if it is negative, that means these are let's say, or the object is slowing down. But if it is positive, that means the object is speeding up, okay? Why? Because these are, so let me just write this one here. So if that is the case, we can say the object is speeding up, right? If that is the case here, we'll say the object is slowing down. I hope you wrote this one. Now, based on this, because the acceleration is positive 10, right, it says the angular speed will do which of the following here. So the question is about angular speed. So if it is positive, that means omega final is bigger than initial, which means that the object is going to speed up in rotation here. Okay, so we have a Wizardi question similar to this, but it says negative. If it is negative, then it must be slowing down here. So the angular speed will do which of the following? Does it decrease? No. Does it stay the same? No. It will increase, of course. Why? Because tangential, or if the tangential is positive or the angular is positive, then we can say the tangential speed increases, which makes the angular speed also to increase as well. I believe this is pretty easy. So I'll just leave this one so that you could solve them here. Now, this page is also very important. There are so many questions in Wizardi that has been basically on this page right here. Okay, so it says correct the following statement. So we have a statement that is incorrect itself, and I need you to correct it for me here. It says the racing car rounds the turn at a constant velocity of 145 kilometer per second. So what does it say? It says a racing car moves or makes a turn at a corner, but this turn at a corner, it happens at a constant velocity. The question tells you the velocity of the car doesn't change while it is making a turn at a corner. What is wrong with this statement? We said velocity is a vector quantity. It has both magnitude and direction. Whichever change, that means the velocity is changing. Here, if you're making a turn at a corner, isn't your direction changing? Yes, if your direction is changing, can we say constant velocity? The answer is no. But instead of this, if the magnitude of the velocity doesn't change, like if the speed doesn't change, we can say the magnitude is constant, which we call it the speed in this case, but not the velocity. So the correct version would be constant speed is constant, not the velocity. All right, we have another question here. It says, describe the path of a moving body whose acceleration is constant in magnitude, all right, at all times, and it is perpendicular to velocity. Whenever it says perpendicular to velocity, we only have one case of acceleration being perpendicular to velocity, and that is centripetal acceleration here. So remember, if this is tangential, this is centripetal, you can see that these two are perpendicular to one another. So it says describe the path. What kind of path is that? That is circular path. But then there is one thing I would like to pay attention to. If they didn't say magnitude, that would be incorrect. Why? Because the direction of the centripetal is changing at every point here. But when we say the magnitude, that means it just how much is the centripetal or the value for the centripetal. That is fine. But so in that case, it is, or in this case, because it will be correct because they say the magnitude. All right, question 11 says an object moves in a circular path with a constant speed. Be aware of this one here. So, and I also need you to write this one for me as well. Whenever it says circular path, there is always a c no matter what. When they say constant speed, that means v initial. It is equal to v final, so there is no tangential acceleration, 0. Okay, and also we can say if it is constant speed, omega initial, it is equal to omega final. Even angular acceleration is 0, even though the question is not about angular acceleration at this point. But make sure you write this one here. Circular path, there is always AC. Constant speed, there is no tangential. Okay, so here's a question. It says, is the object's velocity constant? Because it is moving in a circle here, can we say the velocity is constant? The answer is no. Okay? Because the direction of the velocity is continuously or constantly changing. These are both correct. Part B says, is the acceleration constant? But what acceleration are we talking about? whether if it is tangential is 0, that is no doubt angular is 0, what type of acceleration do we have at this point? Only centripetal acceleration. But is that constant? Again, the answer is no. Why? Because the direction of the centripetal acceleration is also constantly changing here. At this point it is to the left, this point it is, let's say, south, at this point it is, you can say east or right, doesn't matter, this point is upward here or north, you could say. So because the direction is changing, so I cannot even say the acceleration is constant because the direction is changing. So once again, it is not constant because the direction of the acceleration is constantly changing too. All right, we have another question. Says, give an example. This is something very important. Give an example of a situation where an automobile driver can have a centripetal acceleration, so there is AC, but no tangential acceleration. So AT is 0. Isn't this sort of like opposite to the previous one that we have? Okay, so we can have centripetal, right? But then there is no tangential acceleration. In order to have centripetal acceleration, the object must be moving in a circular path, that is first. And then in order for the tangential acceleration to be 0 or no tangential, we said earlier that the speed must be constant. So can we say, for example, an object moving in a circle but with a constant speed? That'll be the correct answer. Once again, moving in a circle, there is AC, right? And then if V initial equal to V final, there is no tangential acceleration. So if that is the case, we can call this constant speed here. So describe the path or give an example of an object that has centripetal but no tangential, that the object must be moving in a circle at a constant speed. Okay. Here's another question which is also interesting. Can a car, an object, move around a circular path so that the car has tangential acceleration, right? That's what it says, but no centripetal acceleration. And it says a car move around a circular track. We said whenever there's a circular track, there's always AC. But the question says, can it have tangential but not centripetal? The answer is no. Because centripetal is necessary. It is crucial to maintain, to keep the object, let's say, moving in a circular path. So that is impossible. So the answer is no, right? Centripetal acceleration is necessary, let's say, for circular motion in cars, let's say on a circular track. This is the question that I mentioned earlier. It says the gas pedal and the brakes, let's say, of a car are used to change the velocity by accelerating the car or decelerating it. So we said once you press the gas pedal, it makes the car go forward or faster, let's say. Once, let's just say it makes the car faster, whether forward, backward, doesn't matter. But the point is it makes the car, let's say, move faster. If you press on the brake pad, it makes the car go slower. Making the car go faster or slower, that means there is acceleration. But here's a question, says, could a steering wheel, right, perform either of these two actions? Could the steering wheel do one of the two? And if you're not careful, you might understand this as, for example, can the steering wheel make the car go faster or slower? You might understand it this way, but that is not the point. The point is the gas pedal makes the car accelerate, the brake pad makes the car decelerate, let's say. Can the brake pad make the car, can the steering wheel make the car accelerate or decelerate? The answer is yes. And how can it do that? Not by changing the speed, making it faster or slower, but by changing the direction. We said if the direction change, there will be acceleration even if the speed doesn't change. So of course the steering wheel can change the direction, which makes the object to have acceleration. So yes, the steering wheel changes the direction of the velocity by changing the direction, which in turn causes the object or causes acceleration here. The last question, perhaps, I believe, says explain the difference between centripetal acceleration and tangential acceleration. We can say angular acceleration, it is the rate of change of object's angular velocity during the rotation. So once again, angular acceleration, we could say the change in angular speed divided by the time, or you can say omega final. You can write this t here minus omega initial divided by delta t here. But this one we said it is the time rate of the variation of the direction of velocity. Once again, just to help you remember, you can use this equation just to help you remember. Otherwise, this is not the equation that we use for calculations or whatever. We'll just say the time rate of the change or the variation of the direction of the velocity. This is just to help you remember the definition better. Otherwise, we do not use this equation. Be careful with angular acceleration measured in radian per second squared, and then this one, centripetal, that is measured in meter per second squared. Radian per second squared, meter per second squared. All right, let's answer a few of those Wazadi question. I believe some of them, or at least all of them, are very important. It says when a body moves in a circular path with a constant speed, remember this, underline this, circular path, that means there's always AC, constant speed, that means V initial equal to V final, that means tangential acceleration is 0, don't forget. Okay, so it says it has tangential acceleration but no centripetal. Does it have tangential? No. It has centripetal but not tangential. This is correct, but let's keep an eye on this. It says it has both centripetal and tangential. That is incorrect. It doesn't have tangential and centripetal acceleration. This is incorrect. So the only correct option is B at this point here. Second part says, give an example of a situation in which an automobile driver can have centripetal, right, acceleration, but no tangential acceleration. Remember, to have centripetal, that means the object must move in a circle, yes? That is what we have. But to have no tangential, okay, but to have no tangential, V initial must be equal to V final, or you can say, in this case, tangential will be 0. So can I say if V initial and final are equal, can we say constant motion here? Yes. So let's see which one of these will be correct. A car moving on a straight path, that is incorrect, because in order to have centripetal, it must be a circle. A car driving in a circle at a constant speed. This one is look good, because a circle, that means AC, constant speed means AT is 0, so this is what is required. C says, a car driving in a circle with a changing tangential. If it is changing tangential speed, that means V initial, it is not equal to V final, so you will end up having tangential acceleration. So this would be incorrect, because the question says with no tangential. So that is incorrect. None of them is also not true. Okay. Let's move to another question here. It says a car moves on a circular path with a constant speed. Once again, once it says constant speed, that means V initial equal to V final, so AT tangential is 0. Which of the following is true for the movement of a car? But don't forget, it's a circular path, so there must be AC. It has only centripetal, it has only tangential, both centripetal and tangential doesn't have. We said it has only centripetal. If an object has tangential acceleration, watch this. So remember the note that I wrote for you. If an object has a tangential acceleration of negative 5 meters per second, we said if negative, that means it is going to what? Because the direction is negative, so at this point here, remember this. We said if the acceleration is negative, that means it is going to slow down. So V final, it is going to be less than V initial. In this case, of course, the object slows down here. What if they're asking for angular? Because these are directly proportional, so we can say omega final is going to be smaller than omega initial, and of course, the object will slow down here. So which one of these would be correct? Remember the note that I wrote for you. That would help you a lot to answer this question here. So if it is negative, so is it going to decrease? It says, let me read the question. The angular speed will do which one of the following here? So what happened to the angular speed? If the acceleration is negative, the angular speed is going to decrease at this point. It stays the same, no. Increases, no. All of them is not true here. Okay, and then this is another question that you could try. It's a bit tricky, so good luck trying this one here. All right, I think that's the end of this session here. Next time, inshallah, we'll talk about causes of circular motion. But let me just give you a quick recap of what was centripetal acceleration. So centripetal acceleration, it is the time rate of the direction, or let's say the time rate of the variation of the direction of velocity. It was always measured was always directed towards the center, and it was measured in meter per second squared. We said the equation for centripetal acceleration will use tangential squared over the radius, or we'll use omega squared times the radius. We had the third equation, which was the least popular. It was omega times tangential here. And then we said that if the object is moving in a circle, there's always centripetal. If it is moving in a circle with constant speed, that means there's no tangential. What do we do if we have both tangential and centripetal? We can find the total acceleration by using Pythagorean theorem, which that would be centripetal squared times, let's say, the radical of the square root of the total acceleration. It is equal to the square root of tangential squared plus centripetal squared. And then regarding the angle, we'll say, or the direction, we'll say tan theta to find the direction of the total acceleration. Theta, it is equal to tan inverse of always AC divided by AT. And then we also said that if the total is given with the angle, then whichever for example, the acceleration is given, we'll either use sine or cosine function to find the acceleration that is required. All right, that'll be the end of this session. Make sure you practice this. I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.